we are letting this A cos omega naught t plus theta is one sample function of the random process. Here if you consider this function, if you plot this, how it will look like? It is a cosine, is it? Like this, it is varying, is it? So this value is equivalent to A, this is minus C. For example, if you are starting at 0, from this to this, if you let this is some t1, from 0 to t1, this is the variation of this function. After this, after t1, how it will vary? In the same manner, like this. So it will vary in the same manner forever. That is, if you know the values of this particular function over a time interval, we can predict the values of this function for the other values. That is, before measuring these values after t1, as per t greater than t1, can we predict what are the values of this? Because we already have the knowledge of the values of the function for t less than t1. Because this is A cos omega naught t plus theta, it is a periodic function. If you know the information about one period, over one period, can we predict what are the other values for the next period? Same values. So here omega naught is a constant, is it? What about theta? Theta is the random variable and A is also the random variable, is it? So for this particular sample function, if the time is varying, A and theta are same. That is the phase and amplitude of this particular A cos omega naught t plus theta are same. Even though the random variable A and theta are the variable, but if you consider a particular single function, single sample function, okay, they are same. Why? Because if you know these values for a particular interval t less than t1, we can predict the values for t greater than t1. So therefore, this function, this sample function is the deterministic function, is it? So therefore, the random process x of t is said to be deterministic. Now if you consider another sample function, so another sample function, again it is cosine, but where it is starting at somewhere here. So therefore, what is the phase of this? The phase of this is different from this, is it? The phase of this is different from this. Similarly, see here the amplitude is this much, but what about the amplitude here? The amplitude is changed. We know this function from this time to this time. Okay. So after this time, how it will vary? What is the phase and amplitude? Same, is it? So therefore, for this particular function, also you know the values for some interval. Okay, we can predict the values for the other interval. Without measurement, we can predict. But if you consider these two combinedly, this is the amplitude, this amplitude different from this amplitude, and the phase of this is different from the phase of this. That is, sample function to sample function, the amplitude and phase are varying. But if you consider a single sample function, that amplitude and phase are same for all times. Following? Similarly, if you consider the second sample function, its amplitude and phase are same for all the times. But if you consider sample function to sample function, there is some variation in amplitude and phase. So that's why this sample function is deterministic, this sample function is also deterministic, and so on. All the sample functions of this random process are deterministic. Okay. So that's why the random process is said to be a deterministic random process. Understood? If you know the previous values of the sample function, we can predict the future values of the sample function. If you consider the sample function, single sample function at a time, but the values may vary from sample function to sample function. So that's why we are calling it as the random process. Understood? For example, if the sample function is like this, this is the sample function, and let this is t1. For t less than t1, this is the sample function. Now, can you predict the values of this function for t greater than t1? We cannot predict because the variation is random variation, is it? So this may be like this, or it may be like this. Any value it can take. So therefore, this sample function is non-deterministic sample function. Similarly, we have another function, another sample function. We know these values. Can you predict the next values? We cannot. That may be like this, in this way. So here, this function is non-deterministic. This is also non-deterministic. So therefore, this is the set of non-deterministic sample functions. So therefore, the corresponding random process x of t is said to be non-deterministic random process. So this is an example of a deterministic random process. This is an example of a non-deterministic random process. So here, the sample functions are deterministic. So we are representing the sample functions or the random process by a mathematical function. But in this case, there is no precise mathematical function to represent. So this type of waveform cannot be represented mathematically. Follow? Now we see the classification of random process into deterministic and non-deterministic random process that we already studied. That is, if the sample functions of the process are deterministic, then the process is said to be deterministic process, otherwise it is non-deterministic random process. Okay. So this is based on whether the sample functions are deterministic or not. And there is another way of classifying the random process. Okay. So we see that this is the sample function of the random process x of t, and this is another sample function x2 of t, and so on. We have some n number of sample functions. So all are functions of time. So the collection of these sample functions is the ensemble of the random process. So these are some arbitrary shapes. So obviously this is the non-deterministic random process, is it? Because the sample functions are not deterministic, because they vary randomly. Even though some previous values, we cannot predict what will be the next value. So that's why all these sample functions are non-deterministic, and the process is a non-deterministic random process. So let we are observing the random process at a particular time instant called t1 and the random variable that is uptime by observing the random process at t equivalent to t1 can be considered as x of t1. Okay. So here, so this is the value that taken by the random process. This is another value. This is another value. So what are these values? We let it as x1, this as x2, and this can be considered as xn. What these x1, x2, so on, xn indicate? So these are the values that are taken by the random variable x of t1. Is it? Now if you observe this, how many values that it can take? So here, these values x1 to xn values may lie in between minus infinity and plus infinity. That is, the values that are taken by the random variable x of t1 may lie in between minus infinity and plus infinity. So therefore, the random variable is called as a continuous random variable. Is it? Is it a continuous random variable? The random variable that is obtained by observing the random process at t equivalent to t1. So here the observation interval is, or observation time is t1, and the random variable that is obtained is x of t1. Is it? So here the x of t1 can take any value because the amplitude of this is different from this. The amplitude of this is different from this. So therefore, the random variable that obtained by observing the random process at t equivalent to t1 can take any value. So therefore, the random variable is said to be a continuous random variable. Now you consider another time instant at which we observe the process. Some other time, that this t is equivalent to some t minus 1. Here also, the random variable that is obtained can be written as t of minus 1. Is it? In this case, what are the values that are taken by the random variable? So this value. So here also there are many possibilities. Therefore, x of t minus 1 can also take some infinite number of values. So here also this random variable is a continuous random variable. So here the random variables that can be obtained from the random process by observing the random process at different time instants are continuous random variables. So therefore, the random process is said to be a continuous random process. Understood this? So this is an example of the continuous random variable. Why continuous random process? Here, the random variables that are obtained by observing this particular random process are continuous random variables. So that's why this particular random process is called as a continuous random process. If you observe, what is the t value here? T can take any value here also. That is, t may lie in between minus infinity and plus infinity. Is it right? So what that indicates? Here t is also continuous. The random variables that are obtained are continuous and t is also continuous. So that's why this particular random process is called as a continuous random process. Understood this? Now you consider another random process in which y1 of t is one sample function, y2 of t is another sample function, and so on. We have some n number of sample functions. Let this is y n of t. So here the random process that we consider is the y of t. Here y of t is the random process, y1 of t, y2 of t and so on, yn of t are the sample functions of the random process. So these are the sample functions of the random process. Now, if you observe the random process at a particular time instant, let we are observing the process at this time instant. This is the time at which we observe the random process. Let it is some at t1. Then the random variable that we obtain is y of t1. Okay. Now, if you observe this, what are the values that are taken by this particular random variable? So, this is one value. So, this is another value. This is one value. So, here the random variable can take either positive or negative values. And one more thing, if you let this is plus 5 and this is minus 5, so the random variable can take either plus 5 or minus 5, or plus 1 or minus 1. So, therefore, how many values that the random variable can take here? There are only finite number of values. Is it right? Otherwise, countably infinite number of values. So, if the random variable is taking finite number of values, the random variable is said to be a discrete random variable. So, therefore, in this case, the random variable that we obtain is a discrete random variable, is it? Follow this? So, here in this case the random process that we consider is called as a discrete random. If the random variables that are obtained by observing the random process are discrete, then the random process is said to be a discrete random. So, this is an example of a discrete random. The first one is the continuous random process. See the difference. First one is continuous random process and this is the discrete random. So, if the random variables that are obtained by observing the random process are continuous random variables, the random process is said to be a continuous random process. If the random variables that are obtained by observing the random process are discrete random variables, then the process is a discrete random. See this random process and this random process. In both cases, the time is continuous. The t can take any value from minus infinity to plus infinity. But in this case, the amplitudes or the random variables are continuous. Here the random variables are discrete. So that's why this random process is called as the continuous random process, and this random process is a discrete random. So now we consider a continuous random process and these are the sample functions. So x of t is the continuous random process, and the sample functions are x1 of t, x2 of t, and so on, xn of t, like this. So here I selected the arbitrary shapes. By the process of sampling, we can obtain the samples of this particular random process. So if we take the samples at an equal intervals of time, let this is one sample that is obtained, and this is another sample, this is the third sample, one more sample, this is another sample. That is at an equal intervals of time, okay, we are taking the samples of this particular function. So let this is the sampling interval Ts. See, the function is a continuous function, it's a continuous time function. Here we are taking the samples in such a way that the spacing between the samples is same. That is, between this sample and this sample, the spacing is Ts, here to here the spacing is Ts, and so on like that. Similarly, we take the samples of the second sample function also, this one. This is one sample. Again the spacing is Ts. So this is one sample. That is, we are taking the samples of the sample functions. Okay. Like this. Follow this. We considered a continuous random process and sampled the continuous random process to obtain a discrete time function. Each sample function now become discrete time function, is it? If you remove that red curve, so by the process of sampling, we obtain a discrete time function. That is, now x of t become discrete time. Okay. So therefore, the random process is called as a discrete time random process. This is an example of a discrete time random process. The discrete time random process can be obtained from the continuous random process by the process of sampling. So here we have a continuous random process. So by sampling, the continuous random process with sampling interval Ts. So this Ts is called as the sampling period or sampling interval. That is, time T is taking only a discrete set of values. In the previous two cases, T can take any value from minus infinity to plus infinity. That is, T is continuum of the values. Okay. The functions that we considered are continuum of the time function, okay, or the time variable. But in this case, time T can take a discrete set of values. So that's why the name discrete time random process. But what about the random variables here that we obtain? If you observe the random process at some time instant t, what type of random variable that you will get? If you observe this particular random process, what type of random variable that you obtain? Discrete. See, the amplitudes are not discrete here. The only time is discrete. Amplitudes can take any value. So therefore, the random variables that we obtain from this particular process are continuous random variables. But the time is discrete. So that's why we are calling it as discrete time. Now we take another random process. Let it be one sample function of the random process. And this is another sample function y2 of t, and so on. We have n number of sample functions. This is the yn of t. Now sample this process at equal intervals of time with some sampling rate or sampling interval Ts. Then let this is one sample that we obtain, and this is another sample. Like this. At an equal intervals of time, obtain the samples. The spacing between the samples is same. Like this. We obtain the samples of this particular random process. That is, each sample function is sampled at an equal intervals of time. So here the sampling space or the sampling period can be considered as Ts. Spacing between the samples is Ts. Now if you observe this particular random process, so now it is discrete time. What about the amplitudes of the samples? Discrete. The random variables that are obtained by observing this particular random process are discrete random variables. T is also discrete. So in this case, both the random variables are discrete and the time is also discrete. So this type of random process is called as the discrete random. So this is the discrete